Before we finish, let's look at a few uses of polarizers. One use is an interesting method of testing materials. Some materials become birefringent when put under stress. By building a transparent plastic model of a structure and then putting it under strain, the patterns can show areas of most stress that are most at risk of failing. The way they get the image of the stress patterns is to have two crossed polarizers with the sample in between them. The first polarizer makes the linearly polarized light that is going to hit the plastic sample. So the sample is a transparent plastic that becomes birefringent under stress. And the change of refractive index depends on the wavelength of the light passing through. So the light passes through the sample, is separated into different wavelengths, and then passes through a second polarizer at right angles. So then all you see are the patterns of the lines of stress in the sample. In a 3D film, there are two separate rolls of film with footage shot from two positions roughly eye distance apart. They're then projected using a projector with two lenses, each one with its own polarizer. The two polarizers are at right angles. Then the glasses you watch the movie with have corresponding crossed polarizers for each eye. So that means the left eye sees only the image from the left lens and the right eye sees the image from the right lens. The two slightly different perspectives are what the left and right eyes would see in reality, and so the brain can interpret that as three-dimensional. Liquid crystal displays use polarization of light. The liquid crystal has molecules that, when there is no voltage, twist the polarization of light 90 degrees. So vertically polarized light going in becomes horizontally polarized by the crystal. Then it will go through the horizontal analyzer. But if you apply a voltage to that crystal, it changes the shape of the molecules so that they no longer rotate the polarization. Now the light is still vertically polarized after the crystal, and it doesn't pass through the analyzer. Then a line will show up in black on the grey background of the display. Another use of polarization is to detect exoplanets. Light coming from stars is unpolarized, but the light scattered off a planet's atmosphere will be slightly polarized. Astronomers hope that in the future, accurate detectors will be able to identify the tiny fraction of polarization in starlight to find exoplanets, and even to test whether its atmosphere contains water vapor. We may also be able to detect the presence of liquid water oceans on a planet's surface using what is called glint. This is just the bright light we see when sunlight reflects off a water surface under specular reflection conditions. So think of it as like a mirror where the angle of incidence equals the angle of reflection. Glint from bodies of liquid, such as Earth's oceans, is highly polarized, as we've seen. The diagram on the right shows glint off water in two orthogonal polarizations. The diagrams on the left show a situation where there is not much wind, but the diagrams on the right show photographs taken during the wind, which disturbs the image. This glint has already been seen in our solar system when a telescope on the Cassini spacecraft observed the glint of polarized light off a lake on Titan, which is one of Saturn's moons. Now, these various uses of polarization could make a good student research project.